Hello, my name is Fuat Furkan Erkeç, and in this video I'm gonna make lab 3.6 Amazon SageMaker generating model performance. In this lab we will evaluate the model that we trained in previous lab and the videos, and calculate the metrics based on the results of the test data. So I'm gonna pause the video in creation phase and then I will continue. Okay, now let's continue. The objectives in this lab: use the test data to generate predictions, generate a confusion matrix from the results, generate performance metrics for the model. So let's go to AWS. And let's go to the SageMaker, then notebook instance. So in this lab we continue the previous labs guided in model 3. We will evaluate the model that we trained in previous models, and we will also calculate metrics based on the results of the data, test data. Introduction to the business scenario. We work for a healthcare provider and want to improve the detection of abnormalities in orthopedic patients. We are tasked with solving this problem by using ML. We have access to a dataset that contains 6 biomechanical features and a target of normal or abnormal. We can use this dataset to train an ML model to predict if a patient will have an abnormality. About this dataset, classifying patients as belonging to one of 3 categories: normal, dyscharnia, spondylolisthesis, and attribute information. Each patient is represented by the 6 biomechanical attributes that are derived from the shape and orientation of the pelvis and lumbar spine in this order. And the following convention is used for the class labels: DH, SL, NO, and AB. So lab setup. Because this solution is split across several labs in the model, we run the following cells so that we can load the data, train the model to be deployed. And by running following cells, data will be imported and ready to use. So let's run these cells step by step. So we import the libraries in here, and we download the zip and load the ARF data to data, and we define class mappers and we train, test and validate in here, test and validate in here, and we use some S3 source here, and training the data, training the machine learning as we do in previous lab. So I'm gonna pause the video while this instance preparing for training. After the training is complete, I will continue. Okay, now the code is completed in upper cells. Now exploring the results. The output from the model will be probability. We must first convert that probability into one of the two classes, either 0 or 1. To do this, we can create a function to perform the conversion, not the use of the threshold in the function. So our threshold is 0.3 in here. And based on the result, we can see that the initial model might not be that good. It's difficult to tell by comparing few values. Now we will generate some metrics to see how well the model performs. Creating a confusion matrix. A confusion matrix is one of the key ways of measuring classification model's performance. It's a table that maps out the correct and incorrect predictions. After we calculate a confusion matrix for our model, we can generate several other statistics. However, we'll start by only creating the confusion matrix. To create a confusion matrix, we need both the target values from our test and data and the predicted value. Test data and the predicted value. So I get the targets from the data frame. Now we can use scikit-learn library, which contains a function to create confusion matrix. We import confusion matrix from sklearn metrics and define a metric confusion matrix test labels and target predicted library. So results will vary, but we should have results that are similar to this example. Okay, we are really close to that one. So the previous table that shows the model correctly predicted 7 normal and 18 abnormal values. However, it incorrectly predicted 3 normal and 3 abnormal in ours 19 and 2. By using Seaborn on matplotlib Python library, we can plot these values into a chart, make them easier to read. And if the chart doesn't display the first time, try another cell again, but as we can see, it's easy. Now we can see the chart, and if these results are good enough for our application, then the model might be good enough. However, because there are consequences from incorrectly predicting normal values, no abnormality was found when there actually was one. The focus should be on reducing this result. Calculating performance statistics. If you want to improve, compare the model to next model that we create, we need some metrics that we can record. For a binary classification problem, the confusion matrix data can be used to calculate various metrics. To start, extract the values from the confusion matrix cells into variables. We use sklearn metrics library and import rock score and rock and awk, and after that running this we can calculate some statistics. In sensitivity, sensitivity is also known as hit rate, recall or true positive rate, TPR. It measures the proportion of the actual positives that are correctly identified. In this example, the sensitivity is the probability of detecting an abnormality for patients with an abnormality. Sensitivity in our code 90.47 something. There is a 90 point that number percent chance of detecting patients with abnormality have an abnormality. Is the sensitivity good enough for this scenario? 90% might be not bad, but we can improve, I think, this value. The next statistic is specificity, which is also known true negative. It measures the proportion of the actual negatives that are correctly identified. In this example, the specify is probability of detecting normal for patients who are normal, and 70% chance of detecting normal patients are normal. Is this specificity too low, exactly right, or too high? What value would you wanna see here given the scenario? So I think we could improve this percentage too, since this is the probability of detecting normal for patients who are normal. And positive and negative predictive values. Precision or positive predictive value is the proportion of the positive results. In this example, the positive predictive value is the probability that subject with positive screen tests truly have an abnormality. We have a precision of 86 point blah blah percent, and we have an abnormality, and the probability that is correct is that percent. The negative predictive value is the proportion of negative results. In this example, the negative predictive value is the probability that subject with a negative screening test really have an abnormality. So negative predictive value is 77.777777779%. You don't have an abnormality, but there's this person's chance that is incorrect. Think about the impact of these values. If you were a patient, how worried it should be if the test for an abnormality was positive. On the opposite side, how reassured should you be if you test negative? So as we can see, 10% and 30% and 14% and 23 something percent about be missing. So for example, we can detect an sensitivity. We have 90% sensitivity for detecting an abnormality for patients with an abnormality, and 70% probability for detecting normal patients for normal, and so on. So false positive rate, FPR, is the probability that a false alarm will be raised or that a positive result will be given when the true value is negative. You have 30% chance to positive result is incorrect. So we are normal, but 30% chance to we can show abnormal. So the false negative rate or miss rate is the probability that true positive will be missed by the test. 9.5 something chance that this negative result is incorrect. So we have an abnormality, but this percent that the we given negative result, but this percent we have a chance to incorrect examination. So false discovery rate, in this example the false discovery rate is probability predicting abnormality when the patient doesn't have one. We have 13.6 something percent we have abnormality, but there's this percent chance this is incorrect. How accurate is our model? The accuracy is 8.3 points, around 9%. In summary, we calculate the following metrics from our model: sensitivity or TPR, specificity or TNR, precision, MP V, and false positive rate FPR, FNR, false discovery rate, and accuracy is that. Record the previous values, then go back to step 1 and change the value used for threshold. And the values we should try are 0.25 and 0.75. So let's first record that values. So we save these results. So let's go and change the threshold to that value, then run these cells again. Let's compare the results. TPR is same, but TNR is changed 10%. Precision is changed. Negative predictive value is changed. False positive rate is changed. And accuracy has fallen 3%. So let's make it 95, then run the cells again. So sensitivity or TPR is lowered, TNR is same, precision is fall, and the accuracy has fall down again. The threshold values make difference, yes, they make. The scikit-learn library has functions that help compute area under receiving operating characteristic curve. The ROC is probability curve. The ALC tells how well the model can distinguish between classes. The ALC can be calculated as we see in next lab. It can be used to measure performance of model. In this example, the higher the ALC, the better the model is at distinguish between abnormal and normal patients. Depending on the threshold, the ALC can change. So let's run this up. The arc is 0.89. So typically the ROC curve is plotted with the TPR against the FPR, where the TPR is on the y-axis and the FPR is on the x-axis. Scikit-learn has a ROC underscore curve function to help generate those values to plot. So here is the ROC curve in here, and true plus positive values, false positive values, and here's the threshold. Update the previous code to use target predicted binary instead target predicted. How does that change the graph? Which is most useful? That's the challenge task. So that's it for this lab, and we can try that challenge if you want to. So this is the end of the video. Thank you for watching.